Hi. Today I'm going to make a movie about nucleophilic substitution reactions, but it's going to be two parts. So this first part is just going to be about nucleophiles in general, and a little bit about a reminder of how you work with kinetics a little bit. So I'm going to start by talking about nucleophiles, and then I'm going to move on and talk a little bit about carbocation stability. So let's start off. So nucleophilic substitutions are a very common type of organic chemical reaction, and they're kind of fundamental to understanding more about organic chemistry in the future. Even if you don't actually do this type of reaction very often, they are really good for learning a lot of different concepts within organic chemistry. So let's begin by talking a little bit about nucleophiles particularly. So as the name implies by nucleophile, nucleophiles, then nucleophiles are attracted to positive charge centers. Not necessarily to the nucleus itself, but to positive charges. The nucleophile then generally is given the symbol Nu and with two dots, for reasons we'll just get into in a minute, and sometimes it's given a little negative charge. Now, that symbol with the nuclear, let's redraw that a little bit larger, Nu dot dot, like that. The symbol itself implies two characteristics that nucleophiles can have. They can either have, and usually one implies the other, but not always, negative charge of some sort. It doesn't have to be a full charge. It can also be a partial charge. Or it has a lone pair of electrons. And this has to do with the fact that many nucleophiles are also Lewis bases. But I'm going to leave that for a different discussion for now. So let's look at some examples of nucleophiles. So some examples of nucleophiles that work for us are the most common then, the one most commonly used are something like chlorine minus, right, which is surrounded by has both lone pairs, right, and a negative charge. And its close relatives in the halogens, right, bromine minus iodine. These are nucleophiles that meet both of the criteria for with both lone pairs and a negative charge. And then we can also take examples like from water. Water has no negative charge, but it has lone pairs. On the other hand, hydroxide ions have lone pairs and a negative charge. And if you go even farther, then you can have situations where you have alcohols, where you have lone pairs on the oxygen. You can even have then a situation like this one. All of these will behave like nucleophiles, because these lone pairs or these negative charges will be directly attracted to positive charges on other molecules or particles for that matter. So in each of these cases. So this is one of the things that you have to have for a nucleophilic substitution. But as the name implies, there's a substitution. So in addition to having a nucleophile that's going to attach itself to something, you also have something that leaves. And so in substitutions, there is always a leaving group. Which I'll call probably the LG in the future. And this is an atom that's leaving. Well, it can be an ion, it can be an atom or ion, or it can even be a molecule in some cases. That is leaving the molecule. Basically, it's being replaced, right? And the leaving groups are often other nucleophiles. So we have to write this really clearly, right? Leaving groups are often, almost always, other nucleophiles. And they've just simply been outcompeted, right? Because that's the other part about nucleophiles. They can have different strengths. So if we look at this series up here with, let's just take the example of nucleophile strength, we can look at then, for the example, the difference between water and hydroxide. And we'll leave it at that because that's enough for us to deal with today, or in this particular video. So obviously water has 2 lone pairs on the oxygen, and it has a partially negative charge because of the difference in electronegativity between the hydrogen and the oxygen. So it's a polar molecule. This is a relatively it's not a very strong nucleophile, particularly in relationship to something like hydroxide, which has, in addition to having 3 lone pairs, it also has a full formal negative charge. So this nucleophile is going to be stronger than this nucleophile, and in fact you have to look at the relative strengths of the nucleophiles to be able to determine which one is going to outcompete. But it's not always just a question of being nucleophile strength. It can be, but it can also be the relative abundance of each of these. So if you put something in water, then there's a really high risk that water is going to outcompete everything, simply because there's a lot more water than anything else if you have it in an aqueous solution. On the other hand, if you have it in a non-aqueous solution or a non-aqueous situation, then water can be a relatively weak nucleophile compared to something else that's in there. So it might act as a leaving group, might just leave. Okay, so that's a little bit about nucleophiles, and if you need to learn more about nucleophiles, I'll provide more information for you for that in another video. So when we talk about nucleophilic substitutions, there are actually 2 types of nucleophilic substitutions that we need to discuss, and they're 2 different types because they have slightly different kinetic properties. And so we have 2 main types of nucleophilic substitution, or substitutions, right? And they are referred to by their names, but I'm going to write here that one of them is what we call a monomolecular nucleophilic substitution, which is given the name SN1. Now, why it's called SN1 is due to the fact that we have the nucleophilic, right, is the N part, and the substitution part is the S. And the monomolecular is then the 1. So monomolecular nucleophilic substitution. Now, what do we mean by that? Well, this idea comes from kinetics, right? So and we'll get back to that in just a minute. So I'm going to talk about kinetics in just a second. The other type of nucleophilic substitution is called a bimolecular nucleophilic substitution, and it's given the symbols SN2. And here I don't have to write the rest of it, but the bimolecular then is the 2 here, right? So that implies that there's something to do with 2 or 2 molecules or something like that. And we'll get to that in just a second. So the idea that comes from kinetics is then that monomolecular reaction steps, or anything that has that name, means that only the concentration of one molecule is involved in the rate determining step. Now, the rate determining step, what is that? Well, the rate determining step is the step in any process that is the slowest step, and because it's the slowest step, determines the rate or the speed of everything else. And if you want a longer discussion about that, there will be videos in the future about that particularly. But in this case then, the rate determining step involves only one molecule. So, and usually when you only have one molecule in a monomolecular, that means then that one molecule, A, is decomposing into something else, into 2 different things. So if you have a monomolecular, anything in chemistry, in kinetics, or at least particularly, then it implies then that A is either decomposing or dissociating, right? It's falling apart. Somehow it's falling apart. And if it's falling apart, then you can write a rate law for this, or a mathematical expression of the instantaneous change in the concentration, or the instantaneous change in rate because of the concentration, in terms of only one molecule concentration. Right? So this is concentration of A, right? And since it's concentration of A, and it's A only once, so it's literally A falling apart. It's not A colliding with A, it's just A just decomposing by itself. Now this is pretty uncommon, but it does occur. It's pretty uncommon for chemical reactions to only be decompositions like this, but as a one single step, the rate determining step, it can happen. So then if we go back and we look at what the second one is, right, the bimolecular, then if this is monomolecular, it relies only on one, then a bimolecular means that the rate determining step involves the concentrations of two molecules. So in this case then, if we make a distinction between this one, we say that, and I'll just write it in a little different color so we don't confuse these two, A plus B react to form C. You could add another one too. It could be dot, 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 whatever. But the main thing is that A and B are colliding or reacting with each other in the rate determining step. So the slow step involves two molecules colliding with each other. So you can write a mathematical expression that represents this. And here you can see then that you have the concentrations of both A and B affect the rate of the reaction. And this is really important because when we get a little bit farther into this, then we're going to have to recognize that this is what's going on. Even though I won't talk about this particular way of expressing it, I won't express it or talk about it in this way again. But this, you can get to the bottom of kinetics by looking at expressions like this one. So the next concept that we need to know to talk about nucleophilic substitutions is then something called carbocation, something called a carbocation, or carbocations in general, and carbocation stability. And so if we want to look at carbocations and carbocation stability, we need to, first of all, we need to know what a carbocation is. And there actually are both carbocations. So carbocation, I suppose it could also be pronounced carbocation, but that just reminds me of people in Louisiana. But I guess carbocation, yeah. Or that song by the Red Hot Chili Peppers, I guess. No, that's Californication, isn't it? Yes, okay. So carbocation stability. Okay, so let's look at a carbocation in general first. So here you have a carbocation. A carbocation then is a carbon that has a positive charge. And I'm going to try to be consistent and circle my positive charges just so that we don't get them confused with plus signs when we get a little bit farther into this. So this carbon is then surrounded by three R groups, and an R group is just a fancy organic chemistry way of saying, like, technically it's called a radical. I've also heard it called a residue. I'm not sure why, but it's also just, you can also say sort of the rest of the molecule in one way, because that's kind of what it is. But the correct term is radical, and radical in this case does not mean some guy who's out on some street corner screaming, or throwing Molotov cocktails or anything like that. In this case, a radical is then, it could be anything as long as it is either begins, well, for H it doesn't matter if it begins or ends, right, because it's just going to be an H, or it can begin, it's anything that begins with a carbon. And so if the R is a carbon, then it can continue with many, many carbons on each of these positions, or it can just end with an H. The tradition is, though, if it is not a carbon or a hydrogen, then you have to write what molecule it is or what atom it is. So that might be like a nitrogen or a sulfur or an oxygen, but then you're supposed to include that. You do not write R if it starts with an oxygen, for example. So then we can talk about the different types, and if you don't know this already, then we need to talk a little bit about then the different types of possible carbocations that there are. So you can have a methyl group that has lost its hydrogen, or a methane that has lost its hydrogen, and you get a methyl carbocation. I'm not going to talk about those today. Then they're highly reactive species, but it's not really part of what we need to discuss. So then you have then a carbocation where the ion or the positive charge is on a carbon that is at the end of a carbon chain. And if a carbon only has one other carbon neighbor, then it's referred to as a primary carbon, or a primary, a first degree, or a primary carbon. And so this is a primary carbocation. If the carbon that has the positive charge has two carbon neighbors, 1, 2, then this carbocation is referred to as a secondary or a second degree carbocation. And then the third case, and the final scenario then, is when you have a carbon with a positive charge that has 3 carbon neighbors. And this is referred to then to 1, 2, 3. And so then this is referred to as a third degree or tertiary carbocation. And so if we go down this list then, it turns out that as we go down from the methyl, or the carbocation, this carbocation up here, to the primary, to the secondary, to the tertiary, stability actually increases. So we can write stability goes up. So this is high, and this is low. And now we need to have kind of a way to explain why this tertiary carbocation, or this type of carbocation, is more stable than the other ones. And there are 2 explanatory models, and there are 2 ways of explaining this. So, and one is a little bit more complicated than the other, but I'm not going to go into the super complicated explanation. So 2 ways to explain carbocation stability. Okay, so one of them is called the inductive effect. And it's also sometimes called induced stability, or that's how you would refer to it. And then the second one is something called hyperconjugation. In reality, they're kind of describing the same thing. They're just, one is a little bit more simple than the other. So I'm going to start with number 1 here. So the inductive effect, and I'll talk about hyperconjugation in just a minute. So let's look at this example here, 1. And let's draw the molecule CH3. And so this is, I'm going to only deal with the tertiary example, but I'll probably maybe mention the other ones in just a second. But I'm probably going to draw this. So in this way, inductive effect then, it says basically that this positive carbon in the middle is going to attract the electrons from its neighbors. And when it attracts the electrons from its neighbors, the more neighbors it has, the more stable it's going to be. If it has few neighbors, then this will not be a stable situation. There won't be enough electrons on the adjacent atoms or groups of atoms in order to stabilize the positive charge. I sometimes call this the Homer effect. And the Homer effect basically is like what? Homer, when he doesn't have something, where does he get it? He gets it from Ned, right? So if he goes over to Ned Flanders, you know, Ned's got all this stuff. We all know about Ned's basement, right? So when Homer doesn't have something, he borrows it from his neighbors. So if you've got electron-rich neighbors, then the electrons, you can borrow from them. If you don't have electron-rich neighbors, then you have no one to borrow from, and so you will not be particularly stable. The second explanatory model or explanatory way of explaining this is something called hyperconjugation. And in hyperconjugation, it requires that you understand that the atoms in any molecule that are covalently bonded, so it has to be a molecule, right, are held together by orbitals or bonds, right? And between the hydrogen and the carbon, you have these what we call sigma bonds, right? They're single bonds, and so these are joined s orbitals, kind of. But for now, we'll just assume that they're sigma bonds. And then on the carbon, there are actually then, this is actually an empty p orbital. And since it's an empty p orbital, and it's got a positive charge here, then what happens is that the electrons from the adjacent sigma bonds between the hydrogens actually move over, and they form a molecular orbital or a bond, a sort of a pseudo bond, where there's a conjugation between these electrons in this orbital, or in this sigma bond, which is also a type of orbital, and it joins together and forms a new sort of hybrid orbital between these empty p orbitals and these hydrogens. And that is then what we call an overlap of the p orbitals, with the sigma bonds from an adjacent atom. And this will become a little bit, this becomes a little bit more important later. So it's not like super vital for understanding what's going to come next, but it can be used as an explanation, a really good explanation for some of the reactions that occur later on in this course. Okay, so to summarize what we've talked about today then, or with this video, is I've talked about what nucleophiles are, the general principles behind nucleophilic substitution, with leaving groups, and with what SN1 and SN2 mean. And then now we've talked a little bit about carbocations and carbocation stability. In the next video, we will apply all of these different concepts to actual chemical reactions. Thank you for watching.